Okay, let's work this little problem here. We got a mass of 0.1 kilograms. It has a charge of 20 microcoulombs and is in a uniform electric field of negative 6 times 10 to the 5 newtons per coulomb. The negative means it's to the left. I drew a little picture of it right here. With an initial velocity of positive 100 meters per second. That is, it's moving to the right. No other forces are acting on the mass, so you don't have to worry about gravity or friction or anything like that. A, what force is acting on the mass? B, what is the acceleration? C, how much was the change in voltage when the mass stops? So we're going to bring it to a stop. So let's set this up with given, find, and solve and all that. Let's just do the given right here. Okay, I'm going to redraw the picture, as I always do. So this is E is equal to 6 times 10 to the 5 newtons per coulomb to the left. To the left. Let me see. All the way up. Okay, that's to the left. Now, the object is right here. We know what the mass is, 0.10 kilograms. We know what the charge is. It's 20 microcoulombs. And we know what the initial velocity is. It's 100 meters per second to the right. And what are we trying to find? Well, we're trying to find the force, the electric force on it, and B, the acceleration, and then C, delta V. What is the change in voltage of that charged particle? Okay. So let's solve it over here. Plenty of room. Well, we want to know what the force is. So here's our little charged particle. And it's in an electric field, so that force will be in the same direction as the electric field. So this is part A. So the electric field, what do electric fields do? Electric fields apply forces to objects that have a net charge on them. That's what they do. And why are these arrows pointing to the left? What do the arrows mean? It means that that force on a positive charge will be to the left. It gives you the direction of the electric force on a positive charge. What if I had made this charge negative? Ooh, that might do that to you on the test. It's going to go to the right. The electric field, if the electric field is pointing to the left, the force on a negative charge would be to the right. That's all. Okay. So, well, this electric force is equal to the charge times the electric field. This is an equation you should add to your equation list and know how to use. So this is going to be 20 microcoulombs. And then and this is negative 6.0 times 10 to the 5 newtons of force per coulomb of charge. Notice that the coulombs cancel. Then I get my calculator out. Oh, there it is. Ugh. All right. And so I'm just going to go 20. And then you got to remember this. What's the micro stand for? Times 10 to the negative 6 times negative 6 times 10 to the 5. And we get negative 12. Did you get negative 12? Okay, good. So the electric force is negative 12 newtons. And what does that negative mean? To the left. That's all it means. Now, for part B, what is the acceleration? Well, the net force equals the sum of all forces acting on the object, and that's equal to ma. But this is really, what I drew up here is really a free body diagram of the object. This electric force is the only force that's acting on that object. So it is the net force. So we're going to say negative 12 newtons equals ma. So A is equal to negative 12 newtons divided by the mass. Well, the mass is given to be 0.1 kilograms. And so a newton per kilogram, the kilograms cancels out, you get meters per second squared. So this is going to give us negative 120 meters per second squared. That's our acceleration. And again, the negative just means to the left. Now, for part C, a couple different ways to do it. You could use this equation right here. We have delta V equals negative E times delta X. Okay, now, and we could do this. We could figure out what delta X is, because we know what the initial velocity is, we know what the final velocity is, and we know what the acceleration is. So we can solve for delta X, and then we know what E is, and we can multiply them. Let's go ahead and do that, even though it's not the fastest way to do this problem. But I don't know time, so I'm going to use the fourth kinematic equation. And so the final velocity is 0. It comes to a stop. So I'm going to say delta X is equal to negative V naught squared. That is, I subtract this the other side, and then I'm going to divide by 2A. So this is going to be negative, and then this is 100 meters per second squared, divided by 2 times A, which is negative 120 meters per second squared. So now delta X is equal to, let's see, that's 100 squared divided by 2 divided by 120, and I get 41.7. Did you get that? Anybody? 41.7, and it's positive. And that makes sense. It's going to go to the right. This is quite a long distance, meters. So now I can figure out what delta V is. Negative, oh, this is going to be a big number. E is negative 6 times 10 to the 5 newtons per coulomb. And then this is going to be 41.7 meters. Negative cancels the negative. I get, so I'm going to multiply that. The answer I got times 6 times 10 to the 5 equals, and I get 2.5 times 10 to the 7 volts. Huge voltage change. Okay. Now, another way of doing it is this. Delta V equals our change in electric potential energy. Hey, what's up?
Can I get that stuff for Thursday?
Please have copies. I'm not going to do all of these, so, but I'm just going to pick a couple of, I'll probably pick one from here and one from here, and then we'll work them out. And then I'm going to put the solutions as a video online.
Great, thank you. Have a good day.
Yeah. Thank you. Thanks for caring, because I'm not even going to grade it, to be honest, but it's not an assignment, but it is to get ready for the AP test, so, okay. And the final.
Thank you.
Mm-hmm. Now, Really, it's a negative loss of, over Q. So this is what now. What was now? Here's why you thinking about energy is going to be easier if you than kinematics. If you look at this guy, it's got kinetic energy, right? 1/2 mv squared. But as the electric field stops it, all that energy is being transferred into the electric field. We're storing up energy in the electric field, because what happens if that thing comes to a stop? But it's still in the field. So what's it going to do? Boing! It's going to push it back. So we're going to get all that energy back. So it's being stored up. So the electric energy that we're storing is equal at the point where it stops to all the kinetic energy it lost. So this is going to be delta K over Q. So what this is K final minus K initial over Q. And, I still need that negative in there. So look, what is K final? And what was K initial? 1/2. I'm just going to go 1/2. I'm running out of room, so I'm not going to write the I'm just going to go 1/2. What was the mass? And the initial velocity? Okay. And then we're going to divide it by the charge. Negative 20, or not negative, positive 20 microcoulombs. Okay? So, if we do this, clear your calculator, I'm going to go minus a negative, so it becomes a positive. We got 0.5 times 0.1 times 100 squared equals, and then I'm going to divide that by 20 times 10 to the negative 6, and lo and behold, I get 2.5 times 10 to the 7 volts. Either way works. Anytime a positively charged object is moving against the electric field, we are gaining voltage. We're gaining energy per unit charge. It's just like if I lift a bowling ball up in a gravity field, I've gained gravitational potential energy, right? Because I'm lifting it against the gravitational field. Well, here this is moving against the electric field. The only reason it could do that is because they had so much kinetic energy and that velocity. And now it's going to take that kinetic energy away and turn it into electric potential energy. You take that electric potential energy, divide it by the charge, you have the electric potential or voltage. Okay. That took a long time. Any questions? Okay. That is all.